So today actually we'll be learning uh, electric field. Okay, today we'll be learning electric field. You have to tell me whether you are able to see my screen or not.
Yes, sir, I can see, sir. Electric field topic in books, sir.
Yes, yes. And my voice is very clear, isn't it?
Yes, sir.
Nice. So Priyadarshini, before I go to your book, I'll just give you a brief idea about field in my presentation. Okay. So let us see what is. It is taking some time to come. An empty slide. Are you able to see? Are you able to see the empty screen?
Yes, sir.
Okay, good. So today we are learning electric field. Okay, so uh, electric field. We have learned electric charges, then electric forces, the Coulomb forces, right? So if you keep uh, two charges, like so they will actually exert a force on like on another. Okay, each other. They will if the charges are positive charges, they will push each other. If the charges are opposite in polarity, then they will pull each other. That means attract each other. Push means repel each other. Okay, so now the question is, so I'll just keep one charge, capital Q charge. Suppose this is at certain distance at origin. So I'll take XY plane or something. Okay. So I just suppose I have a charge Q at the origin and a distance P. This is distance P. Okay, from the origin. That okay. This is suppose this is the P and this at this origin I have kept the capital Q charge. This is a positive charge. I'm bringing another positive charge, small q, over here at this P. And this is a radius vector R. This is the distance between P and this capital Q and small q. Okay, or I can say this is OP. OP is the Poisson vector. OP, which is denoted by R vector. Okay, R vector. So now, since these two charges, like according to Coulomb's law, what we know, what we know, there will be a force experienced by each other, right? If I say the small q in terms of small q, according to Coulomb's law, the small q experience a charge force F is equal to q by 4 pi epsilon naught r square. This is magnitude of the force. Okay, this is the magnitude of the force. Now the question is, if suppose the charge was not there at this position, okay, at P, the charge was not there, so force will not be there, right? If the charge is not there, so force will not be there here, right? Are you agree with me or not? We'll not know whether there is force or not, isn't it? The question is, when the charge, see, small q is brought at r distance away from this charge, capital Q, this small charge is experiencing a force over here at P. But when I remove this charge, suppose I don't have this charge, is there anything at this place? My question is there anything at this place now if I remove the charge? Okay, is there anything at this place? Force anyway we don't experience, because if there is no nothing, so you will not be experiencing a force. So the question is whether this place is having anything. Okay,
No, sir.
the answer is no. Okay, the answer is actually if nothing is there, then when I bring the charge small q, then how is this small q experiencing a force f q q by like f is equal to capital Q small q by 4 pi epsilon r square. If nothing is there in this region, okay, if nothing is there in this region, then how come
It,
this
it
small q
becomes
charge when I am
vastness.
placing it here? Okay, just listen it. Yeah, I'm just going to explain it. What is that? So generally we'll think that there is nothing. But if there is nothing, suppose if it is vacuum, as you are saying, if it is vacuum, when I bring a charge here, it will it will not for like experience a force, right? Will it experience a force if it is simply a vacuum? Will it will it experience a force if it is a simply vacuum or simply an empty space? It will not. It will not experience any force. Okay, so it will be force will be zero if this is an empty space alone. Understand? If it is empty space, it will not experience any force. So what is there then? So in the early stage of development of this electrostatics and electromagnetic theory, scientists, especially Faraday, he had termed that there is something when even the charge is not there, small q is not there is something called field. What is that? Field. What is that? Field is there. So what happens when the charge is brought? This field will interact. Okay, interact. Field will interact or act on Q, giving rise to a force. Understand? So I'll just repeat the whole concept what I am trying to say. If I have a capital Q charge at the origin, okay, and at a distance r distance away, there is a point P in the space. I'm bringing another charge, small amount of charge. I'm bringing over here, and then I see this small charge, like this charge is experiencing a force. Okay, experiencing a force, but we don't know how come the force comes. Okay, how come the force comes? I mean to say, if we remove the charge, whether there is something in this region. If it is simply an empty space, then if I bring the charge at or keep the charge at any empty space, there will be no force experienced by the charge. Okay, so the early days of this electrostatics or electromagnetic theory, Faraday and other scientists, they have argued this phenomena, and then they have arrived to a conclusion that there is something called field. Okay, there is something called field, and since it is we are defining electric, so the field is created by what? So there is something called field. Now we'll see what is electric field. So as I said, if you have a charge q over here, okay, at any distance or at any distance r, you have another small q charge, okay, at p. So what happens? This small q charge will experience a force because of the field created by capital Q. So field will be created by. So what is that? No, this capital Q charge creates a field around its surroundings, around its surrounding. Okay, and when you bring another charge, this field, this field will act on, will act on the Q charge and giving rise to a force, giving rise to a force on it. Okay, on it. Understand? Do you understand the concept of field now? So what is field? Field can be a scalar quantity or vector quantity. It can be either scalar quantity or a vector quantity. And field means how the distribution is with respect to the space. That means this is, suppose this capital Q is creating a field. So how the field is distributed, how a physical quantity. So electric field is a physical quantity which actually is created by a charge around its surroundings, and due to which any other charge when brought into that region is experiencing a force. Understand? So field is the cause for this force experienced by the other charge. So the field is created by capital Q charge. So this is called source charge. Source charge. So the charge which is creating a field is called source charge. And the effect of this field is experienced by this small q charge. That's why this is called test charge. That means we are testing the presence of, or we are able to see the presence of field. Okay? By what? By the small q charge as it is experiencing a force. That's why it is called test charge. What is that called? Test charge. Okay? And field is a quantity that can be a vector quantity or scalar quantity, and it will be distributed all over. Okay, all over the region. Okay, if I say, okay, just let me wrap some of the part. These are all written in your book. I think no need to take note from here, and also I am recording this lecture. You'll be able to get that lecture as a reading material. So this Q is creating a field all around it. Okay, and the field can be a scalar quantity or vector quantity, and in this case the electric field is a vector quantity. Okay, because we'll see how we quantify or express mathematically electric field. So field is a quantity which is distributed all over the surrounding of this capital Q charge. Okay, now as I said, that small q charge will experience a force. So if the field is E, field is actually electric field is denoted by E. Okay, so if the electric field is E, then the force experienced by small q charge, okay, will be F in like E electric field into the magnitude of the state charge. Okay, this is the charge. So EQ or QE, whatever you can write. And since this force is a vector quantity, so see this uh, this electric field, which is actually, which can be defined again, force experienced by unit test charge. Okay, so since the force is actually a vector quantity, so electric field also will be a vector quantity. Okay, that means what? Vector quantity means what? It has magnitude. Okay, it has magnitude as well as direction, certain direction. We'll see that. Uh, okay, let me erase some things. Yeah, I'll erase this part. So how do we define mathematically electric field? We define electric field. See, as I said, the force experienced by the Q charge will be Q into E is the electric field. So force is a vector quantity. So this also will be vector quantity, and we can define this as uh, the force per unit charge. Okay, force per unit test charge. Okay, so this is the electric field. Now, so from here, actually, you can tell me the unit. What will be the SI unit? Can you tell me SI unit of electric field? Priyadarshini, can you tell me
Joule,
from
sir.
here?
Newton,
No,
sir.
no, no. See. This is electric field. The electric field is this. This is the force per. This is charge. Okay. This is coulomb, right? This is Newton and this is coulomb. Okay. So this is Newton per coulomb. Okay. Newton per coulomb. It has SI unit Newton per coulomb. Okay. Okay. Newton per coulomb. So is it okay?
Yes, sir.
Now, yeah. Now there are few points. Yeah. Again, few points to actually know in detail. Uh, those I'll discuss now. So look here, this electric field actually depends. See, the electric field we have defined force per unit charge, right? Force per unit state charge. That means this electric field does not depend on Q. Does it depend? No. And again, I told you that electric field is that can be a vector quantity or scalar quantity, and that will be distributed all over the space, all over the space. And so that means you can understand that the electric field will be having a space variation. It can vary with the space. It can vary with the space. That means the electric field over here, electric field over here, electric field over here, or electric field at very far distance will be not same. They will not. The magnitude will not be the same. Okay, magnitude will not be the same. So it has a space variation. And few more points we will be seeing that I had defined this electric field as the force experienced by unit test charge, that is F by Q. But look here, that the capital Q also will be experiencing the same force, right? Same magnitude of the force in this way. This will be pushed by the small q as it is pushing this way. So this is called, according to, yeah, Coulomb's law, we know that both the charges will be experiencing the same force, and since these are both positive, they will be pushing each other with equal and opposite force. So the capital Q also will be experiencing a force. That means, you know, I said two things. I said that we define the electric field by the force experienced by the stress charge, and I said that electric field vary with the space. Now look, to define the electric field, I have to have my source charge, the capital Q, has to be stationary, isn't it? Otherwise, the definition of the electric field will not be unique at this point. If this is the point, the electric field, the magnitude and direction of the electric field will not be unique at this point if my source of the field is not stationary or not undisturbed. But see here, the capital Q, a small q charge is experience pushing it with the same force. But how to then overcome this situation? So to overcome this situation, what we say in the definition, that the small q charge will be very very tiny or very very negligible. So the appropriate definition of uh, the electric field will be when the charge, small charge or the test charge is tending to zero. It is force per unit charge when the charge, test charge tending to zero. So this is the original or the appropriate definition of electric field. Okay, this is the appropriate definition of the electric field. So all these things are written in your book, whatever I am talking here. Okay, this is the definition. Okay, okay. Now we'll see from your book. Okay, so look here, and yeah. So I haven't defined. See, I was telling that it is the Coulomb force per unit charge. So I'll just tell you here a little bit more. Let me just write what is actually the expression for the electric field due to the capital Q charge. So I said, yeah, that is F by E is equal to F by Q, small q. Okay, this is what I was telling, and obviously there will be limit q tending to 0. Now for the time being, for magnitude, we'll just okay, for the definition purpose we will not consider now this one. Okay, so E is equal to F by Q. What is F? The Coulomb force. What is the Coulomb force between Q and Q at r distance? Okay, this is small q, this is capital Q. What is the force? That is capital Q, small q by 4 pi epsilon naught r square. If you remember, I have taught you. Now see, this is this divided by small q. Okay, so that means what you get? Electric field you get is capital Q by 4 pi epsilon naught r square. Okay, this is the electric field created by capital Q charge. Okay, around it or at this distance, I will say now. Okay, so this is the thing, and you can see this electric field since the uh, okay, since this force is actually acting line like along the line of the along the line joining the two charges, and also you can see we have defined the r as position vector, so it is always radially outward. So it is always radially outward. Okay, this is q, this is small q. So this electric field is always outward, radially outward. And actually, if there is positive charge and negative charge, I'll tell you electric field is directed actually from negative, positive to negative side. Okay, electric field has a direction. Electric field has a direction always from positive side to negative side. Okay, so electric field has positive direction, positive to negative side, or I'll say less positive, sorry, more positive to less positive side. Okay, more positive to less positive side. Okay, so suppose I have here 10 coulomb and I have here some maybe 2 coulomb. Okay, so the electric field will be in this way. Okay, radially outward always. Okay, you just remember, if I have a point charge, positive point charge, so it will be electric field direction will be always radially outward like this for a positive point charge. If I have negative point charge, so how is it look? How does it look? The electric field will be directed inward. Okay, inward. Okay, like this, radially inward. In that case, radially inward. Okay, electric field. And see, we'll say like we'll just discuss again. So electric field actually represent how do you represent electric field? Electric field is represented, since it is a vector, it is represented by a line with arrowhead. Okay, a line with arrowhead. Okay, electric field is defined as with line with arrowhead. Arrow, actually see the uh, the line length, any vector, for any vector, the length of this line will give you the magnitude of the electric field, and direction, this arrowhead will give you the direction of the electric field. An electric field always goes from positive to negative. Okay, we'll see. So these are actually called line, electric field lines. Okay, field lines, these are called field lines. This term was given by Faraday again. Okay, this field line representation. Okay, so yeah, now you just see here in your book, and just see, yeah, so these are the things. And see how electric field vary. Electric field also varies as 1 by r square. Okay, varies as 1 by r square. Okay, so electric field due to charge, positive charge. So here the definition is given. You can see the electric field due to a charge q is numerically equal to the force exerted by it. Thus, the electric field due to a charge capital Q at any point in space may be defined as the force that a unit positive charge. Obviously, the test charge will be positive charge. Okay, unit positive charge. Always the test charge will be unit positive charge. Small q will be unit positive charge, and the force exact like experienced by that unit positive charge test charge actually is defined as the electric field at that point. As I told, see the electric field, this is the 1.9 gives the formal definition. Okay, formal definition of the electric field. Now there are few points. I think I have discussed all these points already. This is okay. I think I have all discussed this up to this point. You just read this, and if you don't understand, uh, like from your book, then you tell me in the next class. I'll just teach you again. Okay, I have discussed all this point. Okay, so electric field is a vector.
Yes.
It can actually, yeah, it can exist in 2 dimension, 3 dimension both. Okay, and one more, I think one more point I have just left out here. I just tell you now. Just hold on for a minute. I'll drink some water. We have seen that the electric field, the expression for the electric field is q by 4 pi epsilon naught r square. So it depends on, say, the q, the source charge, and the distance, right? So the strength is depending on strength, or the magnitude depends on 2 things. One is the which charge is how much amount of charge is creating the field. If this is more, if the capital Q is more, the strength of the field will be more. If less, then it will be less. Okay. Now see this 1 by r square. What does this mean? If I have capital Q charge over here, okay, and I have a distance r, suppose r, maybe I'll just take some 2 3 numbers, so 2 meters suppose, and then I'll take r to maybe 5 meter. Okay, 5 meter away from the charge. So look here, if I think that the test charge is okay, test charge or the electric field, if I want to calculate the electric field at 2 meter away, I have to just here write 2, and I have to write the charge here, like amount of the charge. So suppose 2 meter, this is the r1. Okay, so see the magnitude of the electric field r1. This r1, if I just draw a sphere, okay, draw a sphere with this r1 as radius around, and keeping the charge q at the center. See the magnitude of the electric field at r1 distance at any point, or I say on the surface of the sphere, will be same everywhere. Do you remember? Do you agree with this or not? Because this depends on the distance, right? And the capital Q. Capital Q anyway is same for each distance. So if I just draw a sphere, okay, of r1 radius. So on the surface, okay, on the surface of the sphere, everywhere the field will be the same. Do you agree with that or not? You have to agree. You have to agree. Okay, you have to agree. So if I take another radius, like another sphere of radius 5 meter, okay, that is R2 suppose, okay. So like this, somewhat like this, okay. So this R2 distance from center, so this is again, this is also R2, okay, this is also R2. If I say this is A point, this is B point, this is C point, and this way, this is also R2 distance away, this is suppose D point. So all at C, the field at A, B, and C will be the same. C and D will be the same. Do you agree or not? Because it is just depending on 1 by r square, and I have the distance same on this particular sphere. So the electric field, so from here I can tell you that electric field has spherical symmetry. What is that? Electric field has spherical symmetry. That means what? On the surface of the sphere, electric field is same everywhere. Okay, this is called spherical symmetry. What is this called? This is called spherical symmetry. And yeah, so if you keep, that means what? If you keep a point charge capital Q at the center of a sphere, the electric field created by this particular charge will be same at every point on the sphere, on the surface of the sphere. So that is what it means. So it has, so electric field has spherical symmetry. Okay, this is called spherical symmetry. Okay, now let us go to your book and then see what else we have. Okay, now we'll see. We have seen only for one charge. Okay, only for one charge we have seen. But what about multiple charges? So see, multiple charges, how do we calculate the electric field? That is also very simple. It is the superposition principle. If you remember, we have learned one principle called principle of superposition, that is valid for Coulomb's law. Like when we learned Coulomb's law, we had seen that. Okay, okay. I'll just copy this figure and then explain what is principle of superposition. If you have forgotten or if you have not understood, you will understand again. Yeah. Okay. So see, when this principle of superposition, we are just talking about principle of superposition when there are multiple charges. When there are multiple charges, superposition. Okay. When there are multiple charges, then suppose I have q1, q2, then here q3, q4. These are the charges, and due to all the charges, I need to find out electric field over here at this point P. So how do we calculate electric field for many charges like q1, q2, q3, q4, etc.? So principle of superposition is valid for electric field as well, because we are we are just defining the electric field by Coulomb's force only, right? F by q. So since this is following the principle of superposition, so this electric field also will be the principle of superposition. So what is that? See, when I'll be calculating the electric field for all of them, just by following the principle of superposition, according to principle of superposition, you have to calculate the electric field for single charge, individual charges at this point P. Okay, suppose I want to calculate the electric field at P due to Q1. I'll calculate I1 is equal to Q1 by like E1 is equal to Q1 by 4 pi epsilon naught, the distance between the source charge Q and the test point here, test charge. Suppose a unit positive charge has been kept over here. So this is the source charge, this is the test charge. Okay, so here it is R1P whole square. Okay, this is the distance. So look here, when I was calculating the electric field for Q1, I have neglected the presence of Q2, the presence of Q3, and the presence of Q4. Will not see the effect of these other charges. Not only this, any other charges in around it will not see the effect of that. Okay. Similarly, when I will calculate the electric field due to charge Q2, I'll write Q2 by 4 pi epsilon naught R2P square. Okay, R2P square. So like that, E3 and E4 also will be calculating individually when we don't consider the presence of the other charges. Okay, so we will calculate the electric field individually for each charges at P, and then after calculating the electric field, obviously you have to give the vector sign. Okay, we have to then what we have to do, we have to take the vector sum to get the net electric field. We have to get the vector sum of all of them, vector sum. Okay, so this will be EI. So we have to get the vector sum. Okay, so see, that's why, see, you might be thinking, sir, there is electric field always goes from positive charge to negative charge. Okay, but here there is no negative charge anywhere. So how you are writing the electric field in this way? Look here, the electric field you have to get with proper direction, and then you have to add vectorially to get the net electric field on the particular point, at the particular point. Okay, so in this case you can look the electric field for this Q1 will be in this way, so that's why it is E1, and Q due to Q3 will be this way. Okay, so this is E3, due to Q4 will be this way. Okay, and due to Q2 will be this way, and you have to take the resultant force, resultant electric field, okay, or resultant vector from this. Okay, so then you will get the electric field for multiple charges. So we'll take a few examples, numerical examples, which are already given in your book. So that will help you to understand again in a concrete way. Okay, so this is the principle of superposition. Now, yeah, so now we'll just discuss the physical significance. Then we'll take a few numerical examples from your book. Then we'll stop. So what is the physical significance of the electric field? Okay, I'll just go to the presentation again. Okay, so you can look here. Physical significance, right? So physical significance, we are just trying to understand physical significance. Oh, sorry. Physical significance of electric field. It is written in elaborately, like elaborate way in your book. So I'll just summarize it. So we have defined the electric field as, in the electrostatics, obviously we have defined the force per unit charge, right? This is how we have defined, right? So this is another physical quantity. The force is there already. Okay, charge is already there. We say Q as charge. See here, I know these two terms, right? Force and this is charge. I'm saying that force per unit charge is equal to E. So this is electric field is another physical quantity. But see, in our physics, if we just bring such quantity, like such terms more and more, then it will be, see, someday there will be many physical term, right? So which may not be sometime necessary. Okay, because in this case, look, in the electrostatics, it is actually good to represent the electric field by bringing another physical quantity. Okay, it helps us to understand things. But in the electrostatics, it was not necessary. Electric field was not necessary. That means to term as electric field, or to define electric field by another new quantity, new physical entity E, it was not necessary. Why? Because we know the force, we know the charge. So we can say charge per coulomb. Okay, I'm sorry, force per coulomb. We could have said that. Okay, or charge per unit. Sorry, force per unit charge. We would have said that, but we have given, we have just taken that as a single quantity, or this is a separate physical entity, that is electric field. Okay, electric field. Okay, but why is it justified to define another new quantity in actually, it is not very necessary in electrostatics, but in electrodynamics it is very necessary. That we will be discussing now. See, electrodynamics will be studying, when we will be studying the electrodynamics, you will see both the electric field and magnetic field, they are time varying. Dynamics means what? Time varying. And electromagnetic means you have both electric field and magnetic field vibrating in a perpendicular direction, mutually perpendicular direction, and propagating again in the direction perpendicular to their vibration. That is actually electromagnetic wave. Okay, EM wave, electromagnetic wave. If some electric field is vibrating in this way, magnetic field is vibrating in this way, so electromagnetic wave will be propagating in this way. So anyway, so you look, in case of electrodynamics, so where the electric and magnetic fields are time varying or vary with time, and I have two charges. I have two charges, Q1 and Q2. They are moving. They are moving. Okay, they have uniform acceleration. Suppose they have uniform acceleration. Do you feel these two guys will be experiencing a force or not? If the two charges are moving together, okay,
Yes,
but
sir.
maintaining a constant distance, suppose constant distance. So both of them have a uniform acceleration. Uniform acceleration. Okay, so they will experience a force, right? But they are moving, isn't it? Suppose when this was here, Q was here, Q2, Q1 was here, suppose A, and Q2 was at B. Now see, after certain time, since they are moving with certain acceleration, so after certain time T, the Q1 will be coming here, right? And Q2 will go here. Okay, maintaining the same distance, suppose. Okay, uniform acceleration means they will maintain the same distance. Okay, if they have the same acceleration. So, but still they are experiencing a force, right? Even though, see, they are in motion, they are changing the space. Changing the space, you look here, they are changing the position time to time, but still they are experiencing a force, right? Still they are experiencing a force. But in the nature, like in the nature, see, the experiencing a force means you can say that these two charges are interacting with each other, right? Even when they are in motion. So the experiencing force means they are interacting each other, right? Do you understand that? So they are experiencing force means Q1 and Q2, they are actually interacting each other. Each other, okay, when they are in motion. That means, look, So immediately after like moving to this point, they are not actually, see, no time. There will be no time when they are not interacting each other, even though they are in motion. Okay, that means, see, the information is being carried by the field. Okay, information is being carried by something which has a speed of light. Okay, information is carried by something which has speed of light. That is the fastest speed. Like light has the fastest speed, right? The fastest speed, right? So that's how you cannot understand, like, see, whether they were not interacting each other anytime. So light is like, see, it has a huge velocity. It has the maximum velocity in the nature. It has the maximum velocity in the nature. So far, nothing has been discovered which has velocity greater than light. Okay, so the information is carried by something which is actually having speed of light. And in the electrodynamics, it is said that electromagnetic field. What is that called? Electromagnetic field. So the concept of field, see, so the electromagnetic field which has velocity what? Velocity of light. Velocity of light, which has velocity of light. Understand? Electromagnetic wave has velocity of light. Light is electromagnetic wave, right? In nature. Do you agree? You might be thinking,
Yes.
sir, what you are talking about this thing. I'm not understanding anything, right? I am just trying to make you understand that there is a necessity to define electric field or the concept of field. In the electrostatics, it may not be that severe, but when the charges are dynamics, then what happens? Then the information, they are actually interacting each other. There is no time delay, right? As soon as this like there is no time delay in the like reaction, action, reaction. Okay, between the action and reaction, there is no time delay. So the information is carried by what? Electromagnetic field, which has a velocity c. Okay, and how is it created? Because the charges are accelerated, and accelerated charge particle will create electromagnetic field. Okay, accelerated charge particle will create electromagnetic field. So these are all actually written in elaborate way in your book. You just read this part and then let me know whether you understood why the electric field is necessary to introduce to understand the physical concept. Okay, so electric field, the concept of electric field was given by Faraday in the electromagnetic theory. So, and he proved that by his mathematical formulation, he had proved that that the light is actually electromagnetic wave. Okay, earlier light was not included in the electromagnetic wave, but not Faraday. I think it is Maxwell. Maxwell has given electromagnetic theory elaborately, and Maxwell had concluded that the light is an electromagnetic theory, electromagnetic wave. Okay, light is an electromagnetic wave. We'll read in this 12th standard itself that thing. There is a chapter, I think the 8th chapter maybe, that is the electromagnetic wave chapter. Okay, so we'll yeah, we'll learn slowly. When we come to that point, we'll discuss again. Okay, so yeah, sorry, just a minute. Yeah, this is the book. So this is the physical significance. You just read up to this portion. Okay, since Nikhil is not there, I'll not further extend the study. We'll just take up one numerical example, and then we'll stop the class today. Okay, I'll just tell you the numerical example here. Okay, so look, suppose I have a region here. Okay, So it has uniform electric field. Uniform electric field is denoted by, we'll see next day how electromagnetic field can be represented. Uniform electric field can be represented by arrowhead and the equidistant equidistant line, okay, parallel line. So that represents the uniform electric field. Equidistant parallel line represents the uniform electric field, okay. Oh. Equidistant parallel line represents the uniform electric field, okay. So this, there is uniform electric field, and so this is positive side and this is the negative side. So these are actually two plates. You can say there are two plates. Okay, there are two plates. One is positive plate, another one is negative plate, and that is also maintained by a battery. Okay, by battery. I can change the polarity as well. Okay, I can make this positive, this as negative. If I change the leads battery terminals. Okay. Anyway, so I have uniform electric field over here, and suppose there are two charges. One is electron, another one is proton. Okay, they are, so this suppose this has a distance d. They are actually, suppose the positive, see, you know, like electric field will give a force on positive charge as this QE, and it will actually, so the force on the charge will be along the direction of the electric field. Okay, along the direction of the electric field. Force on the charge will be along the direction of the electric field. Now, if uh, the charge is negative, the force will be, see, the force will be minus Q into E. That means what? This minus sign signify that the force experienced by the negative charges will be in the opposite direction of the electric field. If this is the direction of electric field, so the force will be in this direction for a negative charge. Okay. Now look. So when the proton is just falling from uh, the top to bottom, okay, in between the region of the plate, suppose it is, so the proton is actually dropping from top to bottom, okay. So it takes time tp to reach up to here. Now you just change the polarity. Change the polarity means now you have electric field, uniform electric field, same electric field direction in this way. Now now on electron, since it is negative charge, so it will be going which direction? Electron will go this direction, opposite to the direction of the electric field. This is the direction of the electric field, okay, and electric force will be this way. So electrons will be coming down only, okay, if this is the negative side and this is the positive side, they will come down. And suppose the distance is also same, electric field is also same, and the time taken by this electron to reach from top to bottom is TE. Now they will ask you to find out what is the ratio of TP by TE. Can you tell me? Uniform electric field. Okay, uniform electric field. Can you tell me what will be the ratio? You just think for 5 minutes maybe, or do it if possible, or otherwise, if you are not understanding anything, you tell me. I'll tell you the answer. See, I'll repeat the question. So there is a uniform electric field between two plates. Okay, and the polarity of the plates are maintained by a battery, external battery. Electric field is capital E. Okay, the distance between these two plates are capital small d, and uh, the time taken by a proton to come from, like cover this region, okay, to cover this region d, that takes time tp, and the electron takes time te when we change the polarity of the electric field. So what is the ratio of this tp by te? What is the ratio of the time taken by the proton to the time taken by the electron? Tell me. How do you find out time?
Sir,
Okay, yeah, tell me.
I can't understand, sir.
How do you find out? You cannot understand. Okay, look, how to find out time. So I know the force, right? I know the electric force magnitude of the force will be, suppose proton also has charge E only. So E into small e into E, right? This is the uniform electric field, and it has mass how much? Mass, proton has mass mp. So what is the acceleration? E by mp. This is the acceleration, right? What acceleration of the proton in this electric field? And this is uniform electric field, so this acceleration also will be uniform. Now you know, see what you know the distance or the displacement, you know the acceleration, and suppose the proton started from rest, that means initial velocity was 0. Can you find out what is the time TP taken by this proton to come down from here to here? Can you find out? Can you use, like, which formula you are going to use from kinematics? Since it is
V
uniform
minus C
electric
by
field.
T at the place of
Sorry. Now
acceleration.
I'm going to say I don't know the V, right? I don't know the V. I know that initial velocity is 0. I know the displacement. I know the acceleration. So to find out this time TP, which formula? See, I have three formula. V is equal to U plus AT. I have displacement UT plus half AT square. Okay, and I have B square is equal to U square minus 2 minus
Second
plus
formula, sir.
2as. So which second formula? Because uniform velocity, see, the initial velocity is 0, so this term will be 0. The s is here d, I know. Okay, acceleration I know. So from here, if I find out the time TP, what I get? See, the TP will be, so TP square will be 2s or 2d here, 2d by a, right? TP square will be 2d by a, and a is the AP obviously. So if I just put the value of this acceleration of the proton, this is the acceleration, right? E by mp. So I just put it here. So mp will go up, and this will be here in the down. Okay, E by this. So similarly, if you just use this formula, see, in this case acceleration will be a electron, acceleration on the electron will be ee, again the charge. I'll take the magnitude of the acceleration. So ee divided by me, right? This will be the acceleration. Me is the mass of the, because if the force is E into E, acceleration means force by mass, right? That is the acceleration. So acceleration of the force is same. Okay, magnitude of the force is same. Only what will be difference is the acceleration, because acceleration depends on the mass. If you have a huge body, then it has very less acceleration. Okay, so acceleration I have got. So similarly, I can find out T square is equal to 2d me by E into E. Now, if you take the ratio, I have asked you to find out the ratio of the time. Okay, I hope you are understanding, isn't it? If I take the ratio
Yes.
TP square by T square, yeah, T square, what I get? So TP square means 2d mp by E into E, and here it will be 2d me, here it will be E into E. So E goes off, so 2d goes off, so mp by me. So TP by TE will be root over MP by ME. Okay, do you understand this or not?
Yes, sir.
Okay, good. So look here in the book, you have to put the value of ME and MP and then find out the ratio, or maybe they have asked you to find out only the time, I think, and compare the time. I think they will tell you to compare the time. Look here, it is the case. So time they have asked to find out for both of them. Okay, and take the ratio also. I think you can get the ratio also from there. So like that, you can just read these examples as well. Okay, next day we'll take up this example and then discuss. Okay, I think if you don't see the examples, then your like see the concept will not be uh, strong. Okay, we'll take up this example 1.9 on the next day, then we'll just proceed for the further. Okay, you can also read this. Okay, example, since it is solved problem, just read and see whether you can understand. I will ask on the next day will Wednesday. Okay, so we'll meet again on the Wednesday. That day we'll see this example and then we'll further proceed for the next portions. Okay, so I'll stop it here then today. Priyadarshini,
Yes, sir.
shall we stop it here now? Okay then, good night, bye.
Thank you, sir.